measurement principles. So that book you have already following for the instrumentation devices one most probably. So while we were discussing about the transfer function, so we have assumed that this transfer function to be of the form of second order, and from that we can have the idea that there would be some associated measurement circuit as well. As such, the electrical equivalent of the piezoelectric crystal, there would be some, if we neglect the loss coefficient, it will, and take it as ideal form, it would be a charge reservoir and behave like a capacitor, because basically piezoelectric is made of dielectric material. So, so last day we have discussed about this one, and we were just deriving the transfer function of the piezoelectric sensor. So the sensor in electrical terms behaves like a capacitor. Because it is of dielectric material, because the device is of dielectric material. So if we assume this capacitance to be, let this be Cn, now for measurement purpose, there is for measurement the electrodes are connected via a cable. So this cable has also a capacitance. If we again assume that the resistance effect is negligible, so that series loss or series drop, if we neglect, then we can have a cable of capacitance say C subscript C. The equivalent circuit as given in that Bentley's book is given could be a current source. Actually, the device itself is a charge reservoir, but if we take it as a current source, then we have to write it like dq dt. So current source IN would be dq dt. So this is the current source. So this current source is coupled to the mechanical part. Of course, the charge reservoir is coupled to the mechanical part. We shall discuss this one after discussing this circuit. So this charge, the induced charges due to piezoelectric effect are held across the two electrode by an electrical element Cn. So that is the capacitance of the device. Now this is connected via a cable, so that again if we approximate by another capacitance Cc, so here would be the measurement. Here would be the measurement. So if we neglect this cable capacitance and connect an ideal voltmeter here, ideal voltmeter, D at these 2 points, obviously we will get whatever the charge it is there. So therefore the response of the piezoelectric sensor would be like an ideal one. So that means it will have whatever be the force given, say static force or dynamic force, accordingly it will give a proportional voltage, which is again is dependent on the number of charge that is accumulated between the two surfaces of the electrode. However, in measurement, what will happen? Generally, there will be connecting wires, and to reduce the to reduce the effect of noise, usually it is connected through a cable, and it is done also to reduce the effect of stray capacitance. If you connect two wires, what will happen? The distance between these two wires will vary along the path. So therefore, the capacitance will not be constant. It will constantly vary depending on the position of the wire. So that will create a lot of noise in the measurement. So therefore, usually it is connected through a cable, and then also it is the upper side, that is the cable is wrapped with a ground wire, and then again an insulator. So sheath kind of thing. So two wires, then there is one insulating sheath, then there is one ground wire, and then there is another insulating sheath. That ground wire is grounded at one end. So then we can have, because here our model is a current source, so therefore that is fed to an integrator to make it a proportional charge. And to make this model correct, so there is one parallel resistance which is of very high value. So this is the feedback capacitance, you can say. This is a very high value, maybe 10 megohm, greater than 10 megohm or so. Then of course we can have, because the op-amp can drive this meter, digital meter, whatever of the load here, which could be the input impedance of the voltmeter could be 1 megohm for practical. This is the RL, so voltage V. So this circuit is often known as a charge amplifier because we have conceived this piezoelectric sensor as a current source, and the current is getting integrated here through this capacitance. And because this resistance, parallel resistance, is very high, so it would be it would be like a large time constant integrator. So like an almost ideal integrator. So therefore, it will represent the charge. So which is basically the output of the piezoelectric sensor, the first output. So now this voltage, if we measure, because of this cable capacitance, uh, which is of say some value, a typical value as given in Bentley's book, like this one is 1600 picofarad, and compared to this one is like 600 picofarad. Now, because of this, what will happen? There will be a discharge current. Okay, because of this parallel path, there will be a discharge path of the charge. So, due to this discharge path, if it is not constantly sustained by this source, so then the gain at the output will drop. So that can be derived. So IN we have written as dq dt. IN is equal to dq dt. Now in transfer function form, the rate of change of IN rate of change of IN can be related to rate of change of displacement. Or deformation or strain. I think I have rate of change, that terminology. I think change of IN should be better. Change of IN can be related to change of X. As delta IN by delta X is equal to, again we have used some constant, so C0 say S. In Laplace domain. So we can put a function here S. Now, because we are measuring voltage, So the voltage would be change of VL is delta IN is RL is the load 1 plus RL CN plus CC S. So it is simply dependent on the input impedance of the voltmeter, the cable capacitance, and the capacitance of the piezoelectric transducer. Now, if we go back to our original relation, that where force was applied, so the force is here. So X was F by Ks. So if we now take the change of voltage with respect to change of force, then that will be delta VL, delta IN, delta IN, delta X. We have derived three relations. Applied force is giving a strain X. X, that strain is related to the current source, and that current source is a current source, current from the current source is related to the voltage. So there are three transfer functions here. So that would be simply written by RL by 1 plus RL plus CN plus CC into S. Into this one we have written IN IX C0 into S into, that is the second order transfer function. So into into 1 by omega n square x s square plus 2 zeta by omega n plus 1. So this one can be written as some C0 by small k
Excuse me, sir.
Yes.
Sir, in the third transfer function of delta x by delta f, will the numerator not have 1 by ks?
1 by k would be there.
Yes.
Yeah.
Thank you, sir.
And otherwise this k won't come. So C0 by k, yeah, C0 by k is there. So 1 by small k. Okay.
Sir,
Yes.
sir, how did delta IN by delta X come?
Delta IN by delta x. Delta IN by delta x is C0 into x. So basically this one is coming from dq dt, I equal to dq dt, okay, and q we have is equal to df is equal to c into x, so I is dq dt equal to c dx dt, okay. So therefore delta I we are relating as the rate of change of x, and in the Laplace domain that dt terms are, that means ddt of x is becoming related to the rate of change of the change of current. All
So
right.
what is C0?
C0 is a constant. Basically, it was K in Bentley, a capital K and small k. But here I use this one is C0. All right. This is C0. I equal to dq dt is equal to C0 dx dt. Okay, because last class we have used here a different proportionality constant.
Sir, is that the symbol of a charge source?
Which one? This is symbol of a current source. Current source is essentially a charge source because current is nothing but supply of charge, rate of supply of charge. But by circuit point of view, there is some difference that I want to say here, that as in Bentley, they have given that if you give a static force, you might have gone through it last semester. If you give a static force, then the DC response of this piezoelectric sensor, because of this cable capacitance, is very low, tends to 0. Actually, if I consider, that's why I was telling here, if you consider that you can measure the ideal voltage across this capacitor, then there will be a DC response. Because whatever, if I drive by a constant current source to a capacitor, what will happen? It will be a charge source. Okay. So because it is lossless, so where these charges will go? They will go nowhere. So because of this parallel capacitance, and here we have a RL here, so we will have that DC response coming into picture, which will be evident from the explanation of the transfer function that we shall do now. But if I instead can connect an ideal voltmeter, which is physically not possible, okay, but ideally if it is possible, then we could measure that charge. So in fact, if we have an say very high input impedance, like 10 to the power 13 ohms, 14 ohms input impedance voltmeters are available. Those are called electrostatic voltmeters. So those, if we use here, invariable and measure that step response of a piezoelectric crystal, it will not die down. That is experimentally has been shown. Okay, that it does not die down. It basically stays there. So if you give a static force, there will be a charge difference which will be maintained. And if we, because we cannot measure that charge difference, and here what is our measurement circuit, and which has been given in the books of Bentley and usually used it, is that we have a cable and then a charge amplifier which is converting this current to again through an integrator to a voltage, then, and this one is a voltmeter equivalent, this load resistance. So now if you analyze this circuit, we have this transfer function. Now in this transfer function, you can see there is a S in the numerator. So S in the numerator means basically it's a differentiator. So therefore, what will happen? So that differentiator will do away or kill the zero response, that DC response of the device. So that is the thing. So ideally, actually, we will have a steady state output corresponding to a steady force. But if we want to measure this voltage, then this happens. So we don't have it.
Sir, I did not understand why are we using the voltmeter there.
So because that is we have to for measurement purpose, actually voltage is used. Okay. So now for most of the electronic measurement is done by voltage measurement. Even current is also measured electronically most of the cases through an equivalent voltage measurement.
Oh, so, sir, the voltage that it is measuring is proportional to the charge there, and that is proportional to the force there. So,
Yes. So that's what. So basically, this output VL is the voltmeter output. Okay, and this one, and this is the input. Now this delta F input is first. If we give a force to the piezoelectric crystal, then initially it will produce strain. That strain is related through that uh, elastic tensor, which I erroneously that is S, small s, last class I have referred. I think I have corrected it. You must have seen that I have corrected and sent in the file. Okay. So these corrections I have made in the last class, that S, small s output, where is that? Yeah, this is. Here erroneously I have written stored mechanical energy. Actually stored mechanical energy was this one. So I forgot to correct in the last class. So this is basically elastic compliance. It is similar, it is inverse of the Young's modulus in one-dimensional term. Okay. So that means it relates basically stress and strain. So it is inverse of the Young modulus. It's a matrix. So that's why it is known as elastic compliance coefficient. So Young's modulus is stress by strain and strain by stress is elastic compliance coefficient. Okay,
Sir,
so
can you
now
also show how the second relation came? Delta V by delta I.
delta V by delta I.
Yes, sir.
Oh, I have wrapped it up. Delta V by delta I is coming from the circuit. This is RL. Okay. Here it is, this is the VL. This is VL. Okay. Now this you have I here. Now this is I is coming here. So this I is getting charged a voltage Cn. So SCN is here. So this SCN parallel to SC. So then this becomes SCN plus SCC. Okay. And then if I take this CF is just getting transferred this voltage to this point, then we have RL here. So RL divided by say 1 plus RL plus Cn plus Cc is coming as delta VL by Vn. So if I apply here say a current, and this current will be charging this capacitor. So the voltage available at this point is given by the current IN multiplied by the equivalent capacitor of this one, that is Cn plus Cc into S. So that and CF, so this voltage will be here is the VL. So VL is the I, if I take a current here, IL into RL. So this current IN, so there are three currents. One is going here, charging this IN equal to I1 plus I2 plus I3. Okay, so I3 IN I1 plus I2 plus I3. So then I3 into CF, SCF is equal to I3S into SCF would be this voltage V. So P is, this is the same current will be flowing through this. So I3 amount of current. So I3 IN is equal to I1 plus I2 plus I3. So I3 is equal to IN minus I1 minus I2. I think from this it will come, so I can do it afterwards and show you. Okay, is it all right? So this is RL divided by 1 plus RL into Cn plus Cc into Es. Other way also we can do it, no other way, delta Vn by delta In. Okay, so this output voltage sorry, output voltage I into RL. What is happening? Yes, we can do it other way also. We can get this voltage, input voltage, as IN multiplied by this Cn plus Cc, yes, and then we can get output voltage. That is also possible, but then RL terms will be there. Yeah, RL term can become, so I3 has to be there. So this becomes RL plus CF. Okay. RL plus CF into I3, and this side is yeah. Okay, I shall do it separately. Just take it this relation for the time being now. Okay. Oh, somebody is doing something. Screen is going out. Can you see, or the screen is going out? Is anybody is doing something or what? Hello?
Sir, try to press backspace, maybe.
Back page.
Or press escape.
Huh? Yeah, now it has come. Yeah, from this it can be derived. Just now, most probably, I think I will do it later, maybe next day. So I can show you. So basically, this greater than 10 mega ohm resistance path can be neglected. Okay, and then we have this IN, and again it has gone. Somebody else is doing something, or I don't know how it is happening. I am not able to see the screen. Okay, let me just again, what is happening? Yeah, it has come. Let me complete this one, then I will come back to that. So C0 by K, where I was, 1 by Cn plus Cc. Into RL, Cn plus Cc into S divided by 1 plus RL Cn plus Cc into S into that 1 by omega n square S square plus 2 zeta by omega n into S plus 1 Oops. So if this response is plotted, then it gives like because it's a second order transfer function and it has a resonance frequency, so it will peak at a certain omega n. And then it will drop, and near low frequency its frequency response will drop because of the transfer function that Cn and Cc are coming into picture, the cable capacitance. And we are transferring this current to voltage. Because of these two reasons, actually, this dropping of this thing is there. So this is in log scale. Thousand, etc. So in general, this transfer function of the sensor or the receiver can be written in terms of a time constant. If tau is taken as RL by Cn plus Cc, then Gs is equal to tau s divided by 1 plus tau s. So this is the modifying factor that is coming applied to the device. And this is, of course, the approximate model is to be a second order model. So this is about the receiver part. The transmitter is, of course, will be similar. In the similar fashion, the transmitter part also can be done. So therefore, in the receiver, we can, if we also take into account the if the mechanical response is also taken into consideration in the equivalent circuit. It will be a electromechanical coupled circuit. So that can be represented with an analogous electrical parameters R, L and C, the mechanical. So this is the mechanical part. So where force is applied, and then because it's a second order system, so we will have change of x dot will be there. So this is resistive component will be equivalent to damping. The stiffness is equivalent to a capacitance, and mass is equivalent to inductance. Then this electromechanical energy is transferred to the mechanical energy is transferred to the electrical domain through this dkx dot. That is a current source, and then it charges a capacitor, and then we have current I will be there to, if we have a voltmeter here. So these are basically the electromechanical connection is often represented by a ideal transformer. Now for ideal transformer, of course, DC part can be transported because ideal transformer does not take any current from the source. So in the same fashion, if the transmitter would be just the opposite. So here is a voltage V and the capacitor is here, and then we have the mechanical analogous part represented by electrical parameter. Here there would be the deformation caused by this applied electric volt, which is converted to electric field, and due to the applied electric field there will be deformation, and that deformation is stored here as a dKV. D is that piezoelectric coefficient. So this side we have x dot and then resultant force F. So this is basically the equivalent transmitter. And the other one is equivalent. Receiver. This is these two parts are coupled together. Similarly, here also this is through the electromechanical coupling. These elements are coupled together. So we shall discuss more about this of the device. Yes.
Sir, x dot is like velocity.
Yes, yes. Change in x.
And sir, in
Here
the
we have related change in x, so that's why we have put here x dot.
okay, sir, and in the time constant part, sir, we are doing like RL by CN plus CC. So, sir, won't the unit become like impedance square?
Time constant. Yeah. Time. This is capacitance.
Sir, I mean like we normally do time constant as R into C.
R into C. Okay. It is R into C, but here because this RL is not coming into series. Okay. It is not coming into series or what? I think, let me see, I might have done mistake. Capacitor's equivalent impedance is 1 by CNC, and this point and this point, if it is okay, sorry, I have made a mistake here. It will be RL into RL into CN. Thank you, Sohini. Thank you, Sohini. I just made a mistake here. This RL is coming here. Yeah. It is capacitance, and then if I take this CF to be and a transfer capacitance, so then this RL is in fact coming like this C together can be added, and equivalent R and C are coming in series. Okay, so this is RC only. Okay, thank you. Sorry for the two mistakes I have done here at last day and this one. Okay, and so this is good actually that you are correcting and all those things. Try to also find out this RL by 1 plus RL Cn plus C. I think that can be done easily from if I replace this one by an equivalent impedance, and this side is also like that. then that can be done easily. I think we have to neglect this one as well, then it will be done.
Sir, if we neglect RF and CF, then it is coming, if we consider those in parallel.
Yeah.
Sir, and once, can you please explain that why the frequency response curve is like this? I mean, RF and CF is not playing any role.
No, it is because here what is happening that in the transfer function we have in the numerator there is a s. Okay. So
Yes.
that's why s is a derivative term, and why s is coming? S is coming because of this term, because delta in by delta x is equal to C0s. And so everywhere what we have done, we have convert this charge. Basically charge is produced, and then we have convert the charge to a equivalent current source by dq dt. So invariably the static charge contribution is going out. Because if I give a static force, what will happen? A DC force is given, there will be a charge. Charge is available. But then current will be rate of change of charge. If there is no rate of change of charge, obviously the DC, there won't be any DC response or corresponding to a static force. So because we are converting this charge to current, that's what I was telling, that if I put an ideal voltmeter to measure those charges across the capacitor where no current is flowing, so then it would be done. Then we will be able to measure, or very negligible amount of current is flowing. So in that case, we will be able to measure the charge. So we will have basic effect is that charge will be displaced, and we will have a differential displacement charge across the two surfaces. Now, because we cannot measure the charge easily, so there are certain methods of measuring charge that fundamental methods are there. If those methods are used by reflection charge method, then you will be able to measure the charge. But here we are not doing so. We want to measure it by electronic voltmeters, so that continuous reading etc. can be taken, signal can be transported etc. So for that, this is to be converted to an voltage through a current. So that's why the problem is coming. So we don't have any DC response. I think it is all right. Thank you.
Sir. So, thank you, sir.
You, sir.